Hello and welcome everyone to today's webinar. My name is Tom Sandry. I'm the Workforce Development Training Manager here at Shermco, and I will be your moderator for today's webinar. Our presenter is Mr. Mark Bajowski, our Senior Vice President of Workforce Development here at Shermco Industries. But before we get started, let me do a little bit of house cleaning measures. Let's first talk about participation and interaction in today's webinar. There will be a live questions and answer session after the presentation. And as you are listening to the presentation and developing questions, please enter them into the questions box. We have that highlighted right here. So enter your questions in while they're still fresh in your mind. And at the conclusion of the presentation, we will go down order of the questions and address them to all attendees. Also, everyone in attendance will receive a copy of the presentation and a link to the video recording should you wish to share the presentation with a colleague. Also, you will receive an email within about 72 hours of the presentation. This will serve as documentation of your attendance, and you can use it to earn one continuing technical development or CTD credit with NETA or one professional development credit for your PE. Now, with the house cleaning out of the way, let's go ahead and get started, and I'm going to turn things over to Mr. Bajowski.
Thank you, Tom. Today we're going to talk about a subject that's very important to me and in Shermco in general. At Shermco, we have technicians and engineers working all over North America, as well as many countries. And our workers run into all types of electrical equipment. We work at all different types of facilities. And when we see a facility that's done an arc flash study, it's just a big help. It's a way to communicate to the worker what are the hazards there. OSHA requires that any hazards on a job site be communicated to the workers, and that includes electrical hazards. So doing an arc flash study puts your company ahead of the game, and it lets the workers understand what's really out there. So like I said, we see all different types of sites, different types of studies done by many different engineering companies. Studies should always follow 1584 and NFPA 70E in the U.S., maybe 1584 and Z462, maybe if in Canada, and they should always be completed by a professional engineer. And then understanding what those results mean, and that's what we're going to talk about a lot today, how to reduce incident energy, and then just understanding what the results of a study mean really is important to the worker so that they can understand how to be safe. So first I was going to talk about some key factors that affect incident energy. One of the biggest being time. So once an event happens and a worker's exposed to an arc, how long they're exposed is a big factor into how much incident energy they're actually seeing or being exposed to. And those times can be like 0.05 seconds to 0.3 seconds. But when we talk about time, we're really talking about a very small amount of time in most cases. So equipment performing correctly, having good testing and maintenance done on equipment, a breaker or switch opening slowly can greatly affect that 0.05 to 0.3 seconds that we're typically talking about. So maintenance is very important. All the study is based on time, that everything's working correctly, and the longer the time, the higher the exposure. So this is typically done through relay settings or breaker settings or fuses. And then how much current is there when the event's happening? We're typically going by arcing current, not by short circuit current. And we're going to talk a little bit about the differences between arcing and short circuit current. But how much current is there depends on how quick you get into the curve of the breaker. So settings are very important. Another key factor is distance. how close you are or the worker is to where the event's happening is a major factor in how much exposure that there is to their body. You know, you typically see, I have some examples here, like on the arc flash label, 18 inches where the incident energy was calculated. And that 18 inches, and we're going to go through where that comes from, but typically it's from where the event is occurring to the body of the worker. You know, hands and arms may be closer, so you have to take that into account too, that when these working distances are selected, they're typically selected for how far away the worker would be from the device. And like switchboards compared to panel boards, or switchgear compared to panel boards is much deeper, so you're going to see much larger distances on equipment that is much deeper. You know, so distance is our friend. The further away you can get, the less energy the worker is going to be exposed to. So for instance here, in this example, this arc flash sticker shows the flash hazard at 24 inches. So the engineers selected 24 inches. They came up with 58.6 calories per centimeter. So this is a level dangerous. It's above 40 calories. But it's calculated at that specific point, at 24 inches. If we would move a little bit away, if we double our distance, say at 48 inches, it drops down to 18.8 calories, which is almost a quarter of the original 58. So if you double your distance, your calories go down by the square of that distance, roughly. It's not exact. But distance is so important, and you have to realize every study is done at a distance, and then whatever task you're doing, the worker has to decide, is that distance where I'm going to be? If you're closer, as you can see on the bottom scale, the incident energy goes up dramatically. So if you get closer than that working distance, that should be a red flag to the worker as well. This gear is not dangerous gear. It is dangerous gear at 24 inches, if that makes sense. And those come from IEEE 1584. They give working distances that are typical that most engineers will use for the study. You know, there's all types of gear out there. This is a good start, and this is what most engineering firms use. If your gear's a little different or unique, maybe these aren't the right distances, or maybe if you're doing a task that allows you to be further away, then maybe the incident energy is different than what the sticker shows. Okay, so we want to talk a little bit about arcing current versus short circuit. Arcing current's what's used in the calculations of how quick the breaker is going to trip. An arc is not the same. Arcing current is not the same as short circuit, because in a short circuit, if you have a dead short, the amount of current is really limited to the impedance of the conductors. You're dead shortened. You're going to get all the current you can get based on the length of your conductors and their impedance. Arcing current, it takes some amount of voltage to make an arc. So you're not dead shorted. You got this gap, which takes some voltage. So you're going to have much less arcing current versus short circuit. And we tried to give an example. So, for example, if it takes 100 volts to make an arc on a 40 volt system, you're really only left with 380 volts to pull whatever amount of arcing current would be pulled. And if you look, you know, 100 volts compared to 480, that's about a quarter of your voltage. The same type of arc on medium voltage gear, if it takes about 100, it'd probably take a little more because your spacing would be a little more. But you'll see that arcing current on lower voltages is much different than short circuit. Arcing current versus short circuit current on higher voltages is very similar. So, it's a big difference depending on the voltage. But what studies are based on is arcing current. And like I was saying, that the gap in the space that the arc can occur in depends on how much current would flow. So the bigger the spacing, the less voltage or more voltage drop you're going to have, or voltage difference, and the more or the less current you're going to have. So IEEE 1584 gives, for typical type switchgear and panels, what the enclosure size and this gap should be used in your study. And most softwares, SKM, ETAP, EDSA, all those have those numbers built in. So we did a little example to kind of show the difference. Here we put a panel board and a switchgear on the same bus, and you'll notice that the switchgear had 3,510 amps of arcing current, where the panel, which had smaller dimensions, had more arcing current, less gap. And if you notice, it made the results significantly different. 20 calories per centimeter versus 33.5. So when studies are done, it's very important that the type of gear, the structure, is selected correctly. And then if you have unique things like cable termination boxes that maybe aren't standard, you might want to look at those a little more closely because it could be different. And then when we're talking about construction, there's arc in a box versus arc in open air. Arc in a box, basically all of the energy is projected at the worker, where arc in open air, shown on the right, the arc can go in all directions and only a portion of the energy will be directed towards the worker. So it's another term used, and it depends on the type of construction being used at your site. So we'll talk a little bit, going back to this short circuit current versus arcing current. Over time, engineers have often used what's called infinite bus when doing short circuit studies. Infinite bus basically gives you the worst case for how much current could be seen on your system. That does not necessarily give you the worst case on what arc flash or incident energy a worker would see. So you can't use this infinite bus method alone to get the worst case. There's a paper put out by IEEE where you use the maximum fault current and then you use 50% of the station transformer current. So if your maximum current, if the utility won't give you good information, if you assume maximum current here, the more into this transformer, the more you're going to get out. If you don't have maximum current, you're not necessarily going to have that coming out of the transformer. So if you assume infinite bus, it might throw all your arc flash readings off. So this paper recommends, and most standard engineering software allows you to select this option where you do 2 points. You do infinite bus, and then you do 50% of that, and then you get the worst case, and that's what you use for your arc flash study. So it's just one more thing. If you can get good utility data, that's a big help. But even utilities sometimes are fed different ways, off of different overhead lines. So even utilities can change. So if you're trying to be conservative, you should use this method. And similarly, cable length and impedances matter as well. If you have two motors fed off the same MCC with identical settings, one having a 30-foot cable and one having a 300-foot cable, at which motor would the arc flash be higher? And a lot of people would automatically assume at the shorter one because you'll have more current. That's not necessarily the case because the shorter one might get into the instantaneous setting on the MCC bucket, or the longer one might be just under the instantaneous setting, and it might take a long time to trip. So impedances matter. When studies are being done, we should not just assume some minimal cable length. Cable length should be assumed within plus or minus 20%. Okay, just want to talk about some of the common areas that we find high incident energy when you get your study. Typically between the transformer and the secondary, so where power is coming in, this area, there's no protection between the secondary and the main breaker. So we typically see that to be a very high incident energy. And then same thing when you have an MCC without a main. We see lots of MCCs with very high incident energy. And then especially in commercial buildings, there are some industrial that have low voltage switches feeding the lineup of other switches. Large low voltage switches used as a main, everything downstream of them typically have a very high incident energy. So here's an example of a typical, medium voltage transformer being fed by 13.8, step down to 480. The zone we're talking about is from the transformer to this main breaker. If you see here, this one was estimated at 111.3 calories. That's well over 40 calories, so it's very hard to have protective gear to work on. And these are very common things that we see, throughout the industrial plants. Here's an example with transformer feeding some MCC buckets. Here from the transformer all the way to the MCC, it would be class 4 is what we got when we did this study. So every bucket plugged into either one of these MCCs ended up with a class 4 rating on them. However, if you're just working inside the bucket and you're not getting on these line side stabs, the incident energy was level 2. So if people are troubleshooting overloads or electricians are troubleshooting starters, they're not physically racking them on or off the breaker, off the MCC, then level 2 is enough. But in this case, every bucket was labeled dangerous. It's kind of more about understanding what are you doing, what task are you doing. So with that, let me go back 1 second. So with that, in these cases, and even in the previous case on the transformer, sometimes just writing procedures, you might not ever rack the main breaker off the bus that's dangerous. Or that might be the only task that you want to do. So if you have, let me back up one more time. Here, if you're trying to rack this breaker off the bus, and it's single-ended, you might not ever really need to rack this breaker with it energized. You might be able to come up here to this switch and actually de-energize this whole circuit before you rack it off. If you notice, this switch is a much lower calories. So if you're needing to do a task here, procedures alone might be enough to make this acceptable to work on for the few tasks that you do. Same thing here, procedures to do the task you can do. If the task is to troubleshoot overloads, even though these buckets are labeled dangerous, if the worker knows not to do anything to disrupt or be able to get under the covers of the line side, they're only going to work and troubleshoot the bucket. procedures might be enough to allow them to do their task. If they're going to actually need to rack off and on the MCC bucket, well, that's a whole different item. Similarly, we see high incident energy in commercial buildings that have the 6 disconnect rule. We'll see where they use one piece of gear but no main. They feed the building, and then they have 6 disconnects that feed the building. Those are almost always high incident energy. Okay, so back to the MCC, what could we do? Well, one thing we could do, if we had this scenario where the MCC had high incident energy and we do need to rack on and off MCC buckets while it's energized, we could add a main breaker between the transformer and the MCCs. In that case, this little piece of bus here would still be dangerous, but we can develop settings to make everything downstream much lower. However, that's not always practical. Finding the space to put that breaker can be difficult. When they built it to take as little space as possible. So if we want to add a breaker, we may not be able to on the secondary. We might be able to add one on the primary though. Here, if you notice, we have a fuse switch on the primary. We might be able to remove that fuse switch and install a breaker on the high side and be able to protect on the low side. Fuses have very little selectivity, but if we put a breaker in a relay, we might be able to lower the incident energy enough. And sometimes what we found is that we can actually put the relay in here on the secondary. Sometimes we can't see through the transformer and detect arcing current well enough on 480. So sometimes we might actually put this relay right at the secondary terminals, the CTs, and then go back up and trip this main breaker. This is typically more economical because you're not dealing with the high ampacity bus on the low side. You're typically dealing with medium voltage cables, and you can get a breaker or trippable switch to fit in the same place as existing equipment. So once again, we see on these lineups that have a big fuse disconnect feeding all the other disconnects, we see where the whole bus is dangerous. A lot of times these fuses do have a shunt trip device that allows the fuse switch to be open, but the problem is most of the time it's 6 times rated. So if this is a 2500 amp switch, it's only allowed to interrupt 6 times that current, which is not enough to necessarily open safely under a fault. So it becomes very hard to put a relay, and trip that switch. The best solution again is to go put it in front of the transformer if you can and trip the main, the switch feeding the transformer to reduce those areas. Okay, we're going to talk about a few other items that people use to reduce arc flash current. Zone interlocking, typically used in low voltage like 40 volt gear, is very common. With zone interlocking, if the way it works is if you have a tree of breakers like this being a main feeding 2 feeders, if the main sees the fault, then it's expecting a signal from one of these other 2 breakers saying they see the fault as well. If it doesn't get a signal from either other breaker, then it knows the fault has to be in between the 2 sets of breakers. So when this fault occurs in the zone, since neither one of these would be sending this signal back to the main, it would trip instead of its settings at 0.4 seconds or whatever it's at. It would trip almost instantaneously, which would make the arc flash much less in this area. These work pretty well, and especially newer switchgear. You know, this zone interlocking is a 24 volt typically signal that goes from one trip unit sent to the other. 24 volts is not a lot to work with. If you have bad connections or others, you could have some reliability issues. But typically in newer switchgear, that's pretty well thought out. You can zone interlock from your feeder breakers in your gear down to panels. Same thing, if you zone interlock, one of these two breakers would need to send this breaker a signal if the fault was downstream. So once you get outside of the switchgear, what we've seen is it becomes pretty unreliable. It can be done. I've seen successful installations, but you really have to make sure that your distance doesn't get too far because you're really dealing with a low voltage signal. So zone interlocking, I think, is a pretty good way to reduce arc flash on your main bus in your gear, in your switchgear lineups. Going downstream of that, I think you need to really consider distance and then decide, is reliability worth the benefit that it gives you. On medium voltage, we see bus differential relays, and they greatly reduce the arc flash on the main bus of the switchgear. You know, with the bus differential, here I have a red arrow. Any current coming into this bus must be leaving at one of these blue arrows. So the relay looks for the sum of what's coming in must equal the sum of what's going out. And it can be set very sensitive if those don't add up to trip. So if a fault happened in this zone, in between the CTs, then you could clear this bus very quickly. So this is a big benefit to reduce an incident energy, and especially when you're racking in and out breakers on medium voltage gear. So transformer differential relays are very similar. On transformer differentials, it's really power into the transformer should equal power out. In this case, they wrap the transformer differential from the high side breaker feeding the transformer to the main breaker, secondary breaker of the transformer coming in. So it would greatly reduce the incident energy in this area between the sets of CTs. So transformer differential relays, and we're going to talk about others. You know, they're not easily modeled necessarily in most of the softwares today. Engineers have to kind of do this outside of the software and then manually input it. So it's something that sometimes is missed. You have high incident energy levels in your study, but they might have missed that there are actually differential relays in your system. Another great one is arc flash relays. And what arc flash relays do is, if you're trying to reduce your incident energy, you put basically a fiber loop, something that's looking for light, that's just gathering light. So it's really just a fiber. They have spot sensors as well, but you run some fiber through your switchgear in the areas you're trying to protect. If you have light on that fiber and you have fault current levels, you get to determine what you want to set your fault level at. But if you have high current and light, then this relay would activate and trip whatever device you're tripping. So arc flash relays are very good. They can be misapplied. You have to be kind of careful. These are airframe breakers. That's a 40 volt DS breaker on the left and a medium voltage ITE breaker on the right. These are airframe, so every time they open under any kind of load, because they're breaking the arc in air and they have arc chutes, you'll see the flash does still happen in the cubicle, even though it's in the breaker. So airframe you have to be kind of careful about. Can it see the flash under just normal operation under normal faults? Now these are some more airframe type that would be pretty leery about putting arc flash relays in without some thought. And here's a vacuum type, either a PAL or a GE Power Vac. In the vacuum type, the arc occurs in the vacuum bottle. There's very little chance, there is no chance of the arc occurring during normal operation with inside the cell. So arc flash relays work very well on either SF6 or vacuum type breakers in a cell. You might have to be a little cautious with airframe breakers and make sure that the breaker does not allow light wherever you're putting your sensors. So like I was saying, most of the engineering software does not do a very good job if you put in arc flash relays or differentials. There's not really options. It's really looking for circuit modeling, and a lot of times you have to put in like an instantaneous relay that just models how fast the arc flash relay would work or how fast the differential will work to get it to force it into your times. And I know we had a question, Tom, correct, on how do you model?
Yes. Hang on, let me go ahead and pull that up. The question is, how do you model the Schweitzer 751A arc flash relay?
Yeah, and what I'm saying at a high level, you have to put in basically a dummy device to make it hit that time, and we'll send any of those interested step by step from one of our engineers exactly how we would do that. So we'll get that back to y'all.
Excellent. I'll make sure that I record accordingly.
You know, another item, because racking breakers can be so dangerous, once again, if you can get outside the arc flash zone, anything you can do to that is a really big help. So there's remote racking. Typically, you can get far enough out of the zone. You want a good solid device. There's several companies that make them that understand not over torquing the breaker and not so. But remote racking is a very good thing to help, especially on those cases where you have this real high incident energy on the income of the transformer. There's not a whole lot maybe you can do, but the only task typically you're doing is racking in and out that breaker. So this might be a good solution to get around that common problem. You know, another item that you hear a lot about is maintenance mode. Basically, all maintenance mode is changing the settings from a high-level setting to a lower-level setting. So in maintenance mode, it's either, I prefer some type of switch you switch. That gives an input to your relays or your trip units that, hey, we're going to maintenance mode. We're going to actually change the settings automatically in our protective relay or in our trip unit, and things are going to trip much faster. If you do this, I've heard stories where people left it in maintenance mode, and then when the site came back up, it tripped. If you use a maintenance mode, I highly recommend some type of warning light or beacon going off that, hey, we're in maintenance mode settings, so that people don't walk away, you start back up the plant. The ideal is when you're in maintenance mode, you can lower the settings because all the equipment's not running, and we can not be coordinated in order to protect people's life safety, and we don't want to be left in that mode. And then study assumptions in general. First of all studies are based on the protective devices working as designed. We do find a large amount, especially circuit breakers, that aren't tripping properly. So once again, we're typically talking, 0.05 to 0.3 or 0.4 seconds to trip. If a breaker is sluggish and not tripping, then instead of being 40 calories, if it's twice the time, it could be 80 calories. So, good maintenance is very important. So we should, test and validate. And then, as we showed, there's a lot of things about the structure of the gear, how arc flash relays work, just the whole thing. Engineers that really understand the operation is very key to a good study, and then understanding, what the study is telling you is key for workers so they can make good decisions. As I discussed, you can't say this piece of gear is a Cat 4 gear. It's this piece of gear is a Category 4 at some distance. Or I see a lot on panel boards where electricians are pulling in cable energized. Those calculations typically on the panel boards at 18 inches. If they're pulling in cable and they're physically within 6-8 inches of the bus, the incident energy is much higher at 6 or 8 inches than the sticker shows at 18. So truly understanding what the sticker's talking about, not getting too close to the gear, and or if you're further away, then maybe you can write a procedure to handle it. And then understanding assumptions so that whenever we're making decisions, we understand what the engineer did. A lot of times the engineering firm that did your study can help you kind of come up with, if I'm doing this task at a different distance, what would the arc flash be at that range? So Tom, you said there were some questions?
Yeah, just a couple. We've actually got several questions that we'll start going through the list, but a couple clarifications. I'm just going to take you back to the slide on the the maintenance mode, and let me get to that particular question here. Bear with me. I just had it highlight, and then 4 other questions came rolling in. Okay, would you have to run an arc flash study with the maintenance mode scenario in the ETAP or SKM or EDSA software?
Yes, you would definitely have to run it in both settings. And then, my preference my preference would be that you label the gear without the maintenance mode on, the higher settings.
Right.
And then you're clearly making your procedures. If you turn this switch and you're doing these tasks, it's lowered to this.
Right, so this is actually during your task period in maintenance mode, what your risk is going to be.
Yeah, and showing it. I would label it like your non-maintenance mode. But every site's a little different. That'd be my preference, is always to label it, the worst case, and then have procedures saying if you do this, you can do the other.
Okay. Another is, have any significant impact with the use of exhaust pipes or gas overpressure produced by arc flash?
Is there a study, or can you read it again? I'm sorry, John.
Yeah, it basically just has, have any significant impact with the use of exhaust pipes or gas overpressure produced by the arc flash. So the way I'm interpreting the question is, if you have gas pipes or overpressure in the presence of an arc flash, does that amplify the risk?
I'm trying to help me out, Tom. Can you help me with that question, though? Because I don't understand. If you have, is it flammable, or just if you have?
That's the way I'm interpreting the question is, and then my response would be yes. If you have an arc flash and there are any types of pipes or gas overpressure or anything like that, that can definitely amplify the risk hazard.
Right, and one of the big hazards with arc flash is the pressure wave that it produces. That's why NFPA 70 limits it to 40 calories.
Mm-hmm.
You can build suits, you can build stuff that can protect the body from higher flash, but you also have this big percussion wave coming at you, So I would definitely be worried if that percussion could affect processes, that would definitely be a big concern.
Right.
You wouldn't want that.
Okay. We do actually have quite a list of questions, but why don't you just advance me over to the next slide there, Mark, since you got the control there. Okay. And we are going to go ahead and open it up for questions and answers at this time period. But also, before we start getting knee-deep into the questions and answers, if you enjoyed this topic today for the webinar, we do have some related training offerings at Shermco's Training Services Group, and I have them listed on the board here. If you are interested in either having classroom or computer-based training, just give us a shout at 888-SHERMCO. And finally, coming up next month, we're going to be talking about field testing medium voltage electrical power cables. So, a little bit of highlights of things to come, but Mark, let's get back into the questions. When you were back on the slide where you were talking about the different cable lengths and how this could go ahead and impact your trip times, the one question came in: what standard do you use to get a plus or minus 20% of the length? And are you referring to mainly feeder lengths?
Yeah, I would refer everything to 1584. I have to find exactly where it comes from. But definitely feeder lengths is, when you're feeding one sub to another, we probably normally don't do arc flash at the motors because typically those are de-energized. It's not labeled. But definitely when you have one feeder from one sub to another, all those cable lengths play a big role in what is the actual arc flash at that area.
Okay.
So we'll follow up and we'll get to where the plus or minus 20 comes from.
And also, I know in a past life, helping out with obtaining some cable length measurements during an outage, we actually, since the documentation didn't really show really good cable lengths, we actually used a time domain reflectometer. It's sort of like a cable radar. It sends a pulse down the cable, gets a reflection that comes back, measure the time between reflections and the velocity of the pulse, and it gets pretty accurate lengths of cable lengths.
Right, and that's an optional test for NETA for all acceptance testing. I would highly recommend that we just go ahead and TDR every new cable installed during testing, and then if you're doing maintenance, once again, whatever data you collect and put into the study, garbage in, garbage out. So the better you can make that data, and the more during maintenance that you're collecting that data, maybe you had a study and you're saying, well, I don't really need to collect all that data right now. I would continually collect the data so that when the updates come up, the better that model is, you can see small changes, how it affected it. That's why they use that two methods. So you're doing infinite bus and 50%, so you're kind of getting worst case of 2 points because you have so many possible inaccuracies. Not that the engineer is trying to do a bad job. It's just, like you're saying, getting true cable length can be quite a challenge.
Right. So either you're making an assumption, hoping the draftsman on the one line, if there is even a length on the one line.
So the more we can continually get good data. I know another assumption that's often done is we showed several cases where there's a fuse in front of the transformer. Those are almost impossible to get to with the equipment online, to know what the fuse size is. So what we tell our engineers is to find out if they have spares, to find out with similar transformers. If you're not taking an outage, it's very hard to get that fuse size. And what a lot of engineers will end up having to do, because they have no choice, is to estimate that fuse size based on what should be in there.
Or should be there.
Once again, those are all estimates that can, so the more we can collect data and have a good data batch so that when upgrades come up on our flash study, the better we're going to be.
Again, just sounds like a great opportunity during preventative maintenance time intervals to just maximize your outage with additional information to better your studies.
Yes.
Okay. Here we have another question that came in relatively early in, but what can be done to minimize risk while working or troubleshooting in common high incident energy locations? And I think you covered some of this. One, substitution sometimes, distance is your friend. So can the task be performed using some type of extender poles or to move you back farther? I guess would be one, but I think you mentioned some other different techniques.
Yeah, and another one, it really depends on what the task is and how much risk. You know, the qualification of the person really reduces risk as well. Somebody, whoever's working on something energized or working near energized, first of all, they have to be highly qualified. They have to be able to spot, you know, what's not right. So having someone that hasn't done a lot of this or a lot of whatever that task is, maybe even though they went through book training on this, it's not the same as having experience in identifying what could happen. You know, distance is always the most important. Sometimes you can go upstream and modify settings for the task if you're really having to do something energized. Yeah, I don't know what else, Tom.
Yeah, I think you hit it on the head. I mean, if we just go back to NFPA 70E and Article 110 where they talk about training, basically what it really comes down to is the qualified person with familiarity with the gear, understanding of its operation, et cetera, you know, and then using that information for the risk assessments, conditions of the day, et cetera. Now, you can go into your hierarchy of controls where obviously at the very top, elimination, shut down, don't do the task live if you can avoid it. From there, you can go into engineering controls or substitution methods like, again, getting length, using poles or something would be a substitution method. Sorry, Mark, I'm having a hard time talking. Remote racking would be a substitution method, take the human out. And those are going to be your most effective because they take the human out of the equation. As you move down that hierarchy, you start getting into heightened awareness, administrative controls, and then your final last line of defense is your PPE.
Yeah, and if it's pulling cable into an energized 40-volt panel board, if that was your task that you just felt you had to do with an energized, you know, rubbering off where you can, and then also teaching people, you know, how hazard it is, what you got to do, maybe having a watch to make sure someone's not veering off of what the task is intended to do. You know, those are all very tough decisions. We'd always prefer to do it de-energized, but sometimes that's not possible. And then getting a qualified guy, having written procedures on exactly what has to be done is definitely one of the keys.
Exactly. I think we had a couple other ones in here, Mark. Let's see. Let me get this question right here. I have noticed when looking at our arc flash study, I noticed when looking at our arc flash study that most of the high incident energy areas are in the 480 volt gear. The medium voltage system had very few areas with incident energy over 40 cal per centimeter squared. Is that typical?
Yeah, I think that's pretty typical. You know, if you think of like an arc welder, that's current, right? Not voltage. Arc welder almost has no. So it's just this large amount of current on 40 volt systems that really creates this big hazard. And then also typically medium voltage has quicker trip times, not always, but typically. And then you don't, you know, one thing on the 480, like between the transformer and the secondary, the protection's on the high side of the transformer and it's having to look through the transformer. That fuse was, you know, for the past 20, 30 years was to protect the transformer. It wasn't to protect that low side. So now I think you'll see things change over time, but definitely the 40 volt seems to be where most of the high incident energy is.
Okay. Well, it looks like there's another question in that same vein. We have some areas in our facility where the incident energy is over the 40 cal mark, and the only thing we're doing is operating the switch in those areas. Can we operate a switch that is over 40 cal?
Yeah, so 70E doesn't say you can't operate something or do really anything. It talks about the risk. So to me, if you're operating a device, first of all, if you can put electronic controls or and get out of the zone, that would be the best. If it's a switch and you can't really do a remote operation, then, making sure the cover's good, making sure it's maintained. If there's any thought of the switch having issues, then I would say it's out. You shouldn't be messing with it. A lot of people compare it to driving. We drive to work every day, and we take all these safety measures to make sure we don't get in an incident. But we know driving home today, we could get an incident, and the severity could be death. But we do all these things to limit the risk, or we don't drive. And it's very similar. I think the gear is designed to switch. If you're doing all the things, you're making sure it's maintained, you got someone trained, all the covers are on, and it's designed to do it, I think you could switch. And you could, but I would definitely train people on the hazards and only do people that are highly qualified to do it.
And I think you hit the most important. Everything is always based on the assumption that the switch was installed properly per manufacturer. It is not in an impaired condition. It has been maintained. And that kind of goes with any of the energized work. I mean, all of these studies that we've talked about here is really on that magical assumption. It's been maintained. Breakers have been lubricated. No additional friction in their operating times or anything like that. So that always has to be taken into your feasibility risk assessment is, how well have I kept up on the gear?
Okay.
Let's see. Another one that came in is when equipment can be fed from multiple. When equipment can be fed from multiple sources, say a load downstream of an automatic transfer switch, the values can be much different depending if it is on generator or on utility. Which source should we be using for the arc flash label?
Yeah, so that's a very common question. The stickers we put on the site, do we put them on the normal operating condition? Do we put them on the worst case operating condition? A lot of times we have main tie mains, or maybe you could run with the tie close. Is that what we put on the? So when you get systems that can be fed multiple ways, my instinct is to put the worst case. So like on an ATS, if you're on generator or you're on utility, downstream of that, it might have a huge effect, is what I think they're saying.
Mm-hmm. Mm-hmm.
I would lean towards putting the worst case and then having procedures around so that whenever a worker walks up, they're seeing the worst case and they know they got to go to a procedure book to get around that sticker. If you put the normal, you're not highlighting to the worker that it could be something higher. So to me, I would have a procedure book on these multi-fed systems. I would put the worst case and I would go to a list of procedures that basically say, make sure you're on generator when doing something down here, or make sure you're on what utility, whatever way it would go.
Basically, have some safe work practices
Yeah.
identifying. Okay, we've got one came in here. We own multiple facilities ranging from 200 amp single phase to 600 amp three phase, and many in between. Just as I'm reading, another one popped in, so let me find where I was. Okay, so we have the two facilities, 200 amp single phase to 600 amp three phase, and many in between. Do each of those facilities need to have an arc flash study completed?
Yeah, I think unfortunately the answer is yes. Just because it can be so different, like I'm saying, with just a different size utility, on each one. One might be a 1,000 kVA transformer feeding it, and the other one might be 500 kVA. It can be so unique that I think the safest and the most correct answer is you must have a study done on each one.
I would agree with that. And let's see, the question that came in and bounced my chart up here. Let me read this one. Can you speak to product type and product types and achievement of 0.01 second selective coordination? Is it possible with particular circuit breaker types or only with certain fuses in your experience?
Yeah, I think you're talking about the instantaneous. There are certain breakers. I don't have the list. I know ABB makes a type that's called fast acting, and then most fuses are fast acting. I don't have a list. I think maybe in the question answer we could share some information. I know some of the customers we worked with. We've done some research with them. I just don't have that in front of me, Tom.
Not a problem. The good part about the questions coming in through the question pane is they're all documented. So even if we do not get to your questions, we do have them all documented, and we will do follow-up emails so that everybody's questions get addressed. Ones that we couldn't answer during the webinar, we'll make sure we research and get you adequate answers.
Yeah, so molded case circuit breakers, there can be a big difference in the time, on a dead short, how quick they open, and so you probably want the faster acting to reduce arc flash values, but once again, you have to be in that fast acting zone with this arcing current to even get there.
To achieve, right. Okay, here's a question that kind of falls back to, are there any codes or that specifically state that a study must be done?
Yeah, I don't think there's a code. From what I see over and over in industry is most people refer back to OSHA, and they say if you have a hazard on your site, so if you had acid on your site, sulfuric acid, you have to tell employees how to protect themselves. Electricity is a hazard, and if you don't tell employees how to protect themselves and someone gets hurt, OSHA will come down on you. OSHA does refer in sightings, if you go look at OSHA, they refer to best practices. It's not written in OSHA, but they refer to NFPA 70E.
Correct.
So I've seen too many cases where OSHA's referred to 70E, and if God forbid someone gets hurt at your site, it is going to come up, but OSHA's not going to go look at your site and say, you don't have arc flash stickers, you need them tomorrow. Right. Until something happens. It's just like with sulfuric acid or anything. They're never going to come look for sulfuric acid on your site and say
until the incident occurs.
When something occurs, that's just known that you better have a way to protect the employee from it.
And Mark, as you and I both know, in NFPA 70E, Article 130, work involving electrical hazards, they do specifically talk about two methodologies of determining your risk. One would be if an incident energy analysis study or an arc flash study was done, you would have the labels or the stickers present. But the other is NETA 70E also does provide tables where you can do calculations for selection of PPE. It's a little bit more extensive. You need to try to find your maximum fault currents, your clearing times, etc.
Yeah, so our experience with the tables are for very low commercial end, like say a mall, shopping mall. The tables work pretty good, but any facility of any power coming in, you get above the recommended notes in the tables. So what I see is the tables are only good for very light commercial buildings. You get any kind of industrial, you quickly get above being able to use the tables.
Now, a gentleman did make a good comment. He believes that the new National Electrical Code requires an ARC study. I do recall reference to that. I'm not sure if it's a required or a recommended, but I do know that in the new NEC, ARC study is brought up. And in 2018 70E, they are also now stating that if you did have an ARC study done in the time periods not to exceed every 5 years, you need to review and make sure that they still stand and hold and that nothing has changed.
Yeah, and on that note, it's best if you have a working model of an ARC, because big facilities especially, you're continually adding equipment and changing your model. So we should be looking at doing a continual improvement on your arc flash study.
Absolutely. Mark, I think everything went very well the way you presented today, but it is 2 o'clock on the nose. We've exhausted our 1 hour, so I would like to thank everyone for taking their time out of their busy days to attend our webinar today. Again, come see us again next month. Watch your emails for the registration invites, but we'll be doing field testing of medium voltage electrical power cables. And again, if we did not get to your question, be patient. We have them all documented. We will be following up via emails and get all your questions answered. So I'd like to thank everybody for their attendance, and with that, we will be logging off. Thank you. Have a great day.